We're going to talk about free fall, specifically free fall in general, and then dropped objects. So not thrown, but dropped. First, definition of free fall. Free fall is under the influence of gravity only. So gravity is what causes things to fall. And so free falling means that it is under the influence of only gravity. Specifically, there is no air resistance. So what does this look like? Well, I have a couple of examples to show you. The first is in a location where there is no air, the moon. So this is actually a video that was taken on the moon for Apollo 16, where they did the true experiment of will two objects fall at the same rate if there is no air?
Jim, we copied both solar wind and penetrometer drum in the ETB.
All right, I'm going to fast forward to where they're talking about the hammer and the feather. Here we go.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? That proves that Mr. Galileo was correct in his findings.
I love that. How about that? So what I want to do is look right here. Oh, the reason why he said is appropriately a falcon feather is because their capsule back here that they used in order to get to the moon was called the Falcon. You know, like how for Apollo 11, it was the Eagle. And so each of them had a name from a bird of prey or a raptor. And so this one happened to be the Falcon. And so in his hand over, in his right hand, so on the, there we go. So in his right hand, he's got the hammer, and in his left hand, he has the feather. And then you can actually make sure you look at the ground whenever he drops it. So look around here. And you can see them both hitting the ground right there at exactly the same time. Now, of course, that's on the moon. And a lot of people will say, oh, well, that's the moon. I mean, that wouldn't happen on Earth. Okay, well, let's go to Earth. Now, unfortunately, since I am putting this video up on YouTube, and this is a YouTube video, it won't let me upload the video, my video, with this one embedded. So here's what I need you to do. I need you to go to my eClass page in order to see this video. So to do that, we come here. And if you go under, see right here for week 5, where it says, here's a direct link to videos and simulation labs. This will take you directly to a spot where there is videos. And under Free Fall Dropped Objects 2021, it says YouTube link to the full bowling ball feather in the giant vacuum chamber. And this will take you directly to YouTube to watch this video. I highly recommend that you do this because this video is absolutely amazing. it does drop a bowling ball and a feather in air to show you that the bowling ball hits very, very quickly and the feathers float. And then they close up this giant chamber, pull all the air out, and then drop them again in a vacuum. So very, very much, you've got to watch that video. So make sure that you go here and click on it. All right, now the biggest section that we have some issues with is the math. And so I figured let's talk about the math specifically. First, acceleration. This is how quickly something speeds up. In both of those videos, both on the moon and in that vacuum chamber, what we noticed is that they fell together. They fell at the same rate. Therefore, the acceleration has to be the same. Oh, sorry. There we go. The acceleration has to be the same. It is constant. It doesn't change. The only reason why feathers float is because of air resistance. But if there's air resistance, then there is not free fall. In this unit, we are assuming ideal scenario, which means we're assuming no air resistance, gravity only. And so in terms of this constant acceleration, it has a special name. It is called the acceleration due to gravity. So if I take A, which is our variable for acceleration, and I change it to be the acceleration due to gravity, all I'm going to do is turn this A into a G. So now lowercase g for the acceleration due to gravity is negative 9.8 meters per second squared. When we talked about vectors, we said that those negatives indicate direction. Well, which way does gravity pull? Down. And so the negative here for negative 9.8 indicates a downward direction. So these things will speed up as they are falling. Now, if we are looking specifically at dropped objects, if you see this word, that means, number one, that you have G is negative 9.8 meters per second squared, because obviously gravity is affecting it, which is why it drops. The other thing we know is that it is let go, not thrown. Dropping means you just hold it and you let go. Therefore, the initial velocity is going to be 0. So this one little word, dropped, will automatically give you 2 knowns in the givens box, G and VI. Now, what equations are we going to use for this? Well, we're going to use the equations for acceleration, the big 4. Here are the 3 of the big 4 that have an A in them. Remember, A is the acceleration due to gravity when we are talking about things that are dropping. So anywhere we see, sorry about that. Remember, anytime we see that A, what we should think is the acceleration due to gravity. And so it says here to change A to G. So anytime we see an A, we automatically change it to a G because it is the acceleration due to gravity. Now, let's do some examples. I love the movie Moana. And this is the scene where Maui and Moana climb to this ridiculously tall cliff island. And up at the top, Maui opens up an entrance to Lalotai, the realm of monsters. And so then he jumps in. He's like, don't worry, it's much further than it looks. And then he goes, Yahoo! And jumps in. Well, me being a physics teacher all the time, when I see this scene, all I can think of is, oh my gosh, this would be a perfect example because you can actually hear when he hits the water. You'll hear the splash. And so I took a timer and I actually timed how long it took for Maui when he jumped in. So he started to fall to hit the water. That happened to be 8.7 seconds. So this is actually a number from the movie. All right. So how do we solve these things? Notice we got our 4 boxes. The first one is the givens. And then this is the equation. These first 2 boxes, this is the physics. The last 2 boxes, that's the math. So let's start with the physics. When we're doing acceleration problems, we're always going to write the same 5 variables. D, T, VI, VF, and A. Now, since he is falling, then we know A, the acceleration, is going to be acceleration due to gravity. So we always know this number, negative 9.8 meters per second squared. Now, since it didn't use exactly the word drops, I did make sure in this example that I say right here, his initial velocity is 0. And so that goes here. And let's see, we have 8.7 seconds. Seconds measures time. So now the question is what are we looking for? How far has he fallen? That is our displacement. Now that we have our variables here, we know we do not need VF and we don't care about VF. So we're going to cross that one out. Then we go to our equations. It needs to have D, T, VI, and G. All right, let's see. Well, this one has VF, so we're not going to use this one. This one also has VF, so we're not going to use that. Well, I mean, that leaves one, doesn't it? Which is this one. The D equals VIT plus 1/2 GT squared. On the equation sheet, it's flipped. 1/2 AT squared plus VIT. It just so happens the way that I have it written here, but this is the form right here that you see on the equation sheet. So let's use that one. D equals 1/2 AT squared plus VIT. A becomes G. Now it's time for the math. I'm going to use a different color for it. So this is plug in, and then this is final answer. So for plugging in, we're looking for D equals 1/2 G is negative 9.8 times T squared, 8.7 squared, plus VI is 0 times 8.7. Now, if you are okay with algebra, and at this point you know exactly what to do with an equation, you're welcome to fast forward, okay, to see the final answer. Make sure that you do it yourself as well and get the same answer that I do. If algebra is an issue for you, I'm going to go step by step on how to do this. So the first thing I'm going to do is I'm going to square this 8.7. All right, so I have D equals 1/2 of negative 9.8. And if I put 8.7 squared in the calculator, I get 75.69. On this second part, 0 times anything is 0. So that actually drops out. Well, that's nice. Next step is, now why don't I add, let me put these two together, okay? So it's 1/2 times negative 9.8. If I put that into the calculator, I will get negative 4.9. Excuse me. And then that is times 75.69. Now, if you want to just do 1/2 times negative 9.8 times 75.69 in your calculator, you can do that as well. But again, like I said, I'm going step by step through this to make sure that everyone will hopefully get the right answer. So if I now multiply the negative 4.9 with the 75.69, I get a final number of 370.881. Now notice we're looking for D, and this equation happens to be D equals. So we did not have to do any algebra here in terms of like moving things over. We just kept doing the math and we got a number. So our final answer here, oh, that's a negative, is negative 370. And honestly, I would round to 0.9. For the unit, we have meters per second squared, and so this displacement is going to be in meters. Now, why is it negative? The negative means that he went down. So negative means down 370.9 meters. All right, let's do another one. This one is, how fast was he moving when he hit the water? So this is a second part to this Maui problem. So what I'm going to do is go back to my physics color. D equals T equals VI, VF, and A. A is G, negative 9.8. VI is still 0 meters per second, and T is still 8.7 seconds. Well, since this is part 2, we do actually have the displacement now. We have negative 370.9 meters. The only one we don't know now is VF. Since there's not one that's crossed out, what this means is I can go to this list and I can pick either one of these that has a VF in it. On the equation sheet, this one is VF equals AT plus VI. And then the VF for this one is the same. Now, in all honesty, since we don't have to, I would choose this one because there's no square, so we don't have to worry about square rooting. But if you were to use this one and solve it correctly, you would get exactly the same answer. It doesn't matter. I'm just going to go with the one I think is easier to solve. And so that would be VF equals AT plus VI. A becomes G. All right, now it's time for math. Let's see, this is our unknown. So once again, we're not going to have to rearrange anything, are we? So VF equals, see, G is negative 9.8 times 8.7 plus 0. Well, 0 is just 0, so that goes away. And so all we have to do is negative 9.8 times 8.7, and that gives us negative 85.26. Now, what is the unit? Well, we've got meters and seconds, and plus VI is meters per second. So VF is also going to be meters per second. Well, what does that negative mean? This means he is going to be going 85.26 meters per second downward. All right, why don't we do an example where we are actually going to have to do some algebra? So let's do that. All right. Observation deck of a tall skyscraper is 370 meters above the street. Determine the time required for a penny to free fall from the deck to the street below. All right, let's start with the physics. D equals T equals VI, VF, and A. A becomes G and negative 9.8 meters per second squared. So the penny is free falling, and so initial velocity is 0. Let's see, what else do we know? Oh, we've got this 370 meters, right? So the penny is going to start 370 meters above, which means it's going to fall 370 meters. All right, so here is a person at the top of the skyscraper holding this penny, and so this is 370 meters above. Well, the penny is going to be going down 370 meters. That's why I put the negative there. It's displacement. And let's see, what are we looking for? Oh, determine the time. All right, so this is our question mark. So what are we going to mark off? We're going to mark off that VF again. Well, there was one equation that dealt with this if there was no VF, and that's that D equals 1/2 AT squared equation. Hopefully by doing a few of these, you'll see the pattern, okay? If time is involved and you cross off the VF, it's this equation. A becomes G. All right, well, look here. We have D. So now it's time for the math. Let's change colors here. Negative 370 equals 1/2 of negative 9.8 times t squared plus 0 times t. Now, some people get freaked out about this whenever they see that there's a t squared and a t, but what is 0 times anything? It's 0. So that goes away. So we're left with negative 370 equals 1/2 of negative 9.8 times t squared. Well, that makes this a little bit better, doesn't it? All right, the next step I would do is the half of negative 9.8. So half of negative 9.8 is negative 4.9. So you would do 1 divided by 2 times negative 9.8. And you get negative 4.9. All right, now we need to get t squared by itself. We need to get rid of this negative 4.9. Notice there's parentheses around this t squared. This means multiplication. And so it's negative 4.9 times t squared. So to get rid of the negative 4.9, we have to divide by negative 4.9. So negative 370 divided by negative 4.9 gives us 75.51. The 4.9 cancels on the other side. We're left with t squared. Well, if we need to get t by itself, we need to do the opposite of squaring. The opposite of square is the square root. And so we get t equals 8.69. And so our final answer will be 8.69 seconds, because time will be in seconds. All right, let's see. Last one is determine the speed it would hit the ground. All right, let's go back for physics. D, T, VI, VF, and A. A is G, negative 9.8 meters per second squared. VI, 0 meters per second. Let's see, we had D, that was negative 370 meters. And now we have time, 8.69 seconds. It says determine the speed it would hit the ground. And so if I were to draw my little picture here again, happy doing physics. There's my penny. It starts up here at 0. And so we are looking for the final when it hits the ground. Now remember, I said if you've got all 4 of these, you can use either equation that has VF in it. VF equals AT plus VI, or VF squared equals VI squared plus 2AD. Since I already did this one, I'm going to do this one instead, okay? But you can go ahead and try this one out, and you should get exactly the same answer that I do. All right, so here we go. VF squared equals VI, which is 0, squared, plus 2 times A, which is negative 9.8, times D, which is negative 370. All right. Well, why don't we multiply these things together, right? 0 squared is 0, and so this is going to go away. 2 times negative 9.8 is negative 19.6 times negative 370. And so now we will multiply those two together. And we get VF squared, and 2 negatives make a positive 7252. Now we have to do the opposite. The opposite of squaring is square root. So if we take the square root of both sides, we get a VF of 85.16. Now, if you use this first equation here, this VF equals AT plus VI, you should get negative 85.16. So here's one of those things from math. When you take the square root of something, it leaves it as a positive or negative 85.16. Well, since it's falling, that means it's going to be the negative. Oh, I forgot to do that in green. I am so sorry. So I'll tell you what if we at least do the final answer here? So the negative. So negative 85.16, and V is meters per second. All right, those are all of my examples that I have for you. Please, please, please make sure that you ask questions and you help each other out and you come for help tutoring to any of us that are teachers to try to make sure you get this. The only way to make sure you get this math is to practice. So please make sure you are practicing. Let me know if I can do anything to help.